We shall start electrostatics and dielectrics. Um, Before going into the subject proper, let me discuss what we have in electrostatic and vacuum. In electrostatic, while dealing in electrostatic or vacuum, we assume that there are certain charge distribution which we can choose at our will, and we found out the field or potential at an external point having position vector r with some with reference to some suitably chosen coordinate system. So the task in electrostatics in vacuum is to find out the field or potential at a point due to this. Now, whenever we come across a problem of evaluating field or potential at a point in presence of a material body, the situation gets changed. Consider we have a material body placed over here. So the charges um, uh, the charge distribution that we selected at our wheel produces a field in its neighborhood. That field also operates on the material over here. This material is ultimately made up of atoms or molecules, which in turn is made up of charged particles, electrons and protons. Under the action of the field produced by this charge distribution, the electrons, the positive and negative charges experiences field in opposite direction. That is, the charge distribution of the material body will undergo a change, and this change body will contribute some amount of field quantity at the point of observation. That is to say, if we want to find out field at this point, the field R at point R has two contributions. One is the field that we had in vacuum plus the field that is obtained from the due to the material body. This here we have used the principle of superposition. Now consider one more thing. The charges that we selected at our wheel is the charges on the conductor, and a conductor is characterized by the plenty of free charges. If we consider a metallic conductor, in metallic conductor the atoms are stacked in a periodic manner and they are very close to each other. The valence electron of the atom forming this metallic conductor do not belong to particular atom or the parent atom. Rather, this valence electron moves around all along the metal, and the only restriction is that they cannot escape from the metal due to the barrier potential. Since the number of atoms is very large, of the order of Avogadro number, and if one or two electrons are contributed from each atom, there are plenty or enormous number of free electrons present in a conductor. In other type of conductor, the charge carrier may not be electron, but there are plenty of charge carriers. In that sense, the field that is produced by the charge distribution that we selected at our wheel may also be called the charges due to a field due to the free free charges. The F stands for free. This V was for vacuum and this F is free. These two suffixes will be used frequently, and they have the same meaning. And this M is the denotes the material. Now the material body. Now come to the material body. The material body may be of two kinds. One is conductor that I have just talked about, and another one is called the insulator. The insulator is different from metal or conductor is that in insulator there is no free electron. That's why they cannot almost conduct electricity. In an insulator, the electrons are strongly attached to their parent atom and molecule so that they cannot move around the insulator as a whole. Rather, they remain attached to the electron to the atom, so that under the influence of some external field they can move only by a small distance, a distance even a fraction of in atomic dimension. That's why in that sense the field that is produced, that the EM field due to the insulator or dielectric may also be called as the field due to the bound charges, because they are called bound because the electrons are within a dielectric, they are not free to move around, they are bound. In that sense the field may be, we may call the field to be the atom field plus the material field, or we may call it the field due to free charges and due to the bound charges. In electrostatics of Part-1, we have learned how to calculate this. Now in the electrostatic of dielectric, our aim will be to develop technique for the evaluation of this part. So this is the main objective of electrostatics in dielectric. Now the situation, if you look into the situation is very complicated. Firstly, in a dielectric we have atoms or molecules. The electron moves around the molecule. Atomic nucleus, the electron moves around the atomic nucleus, and there are other neighboring atoms forming the dielectric. If we consider the field, the electron here experiences a strong field in the neighborhood of the electron, and the field goes to zero over outside the atom. Again, for the next atom, the field will here the field is like this, and for the next atom the field will be there, and this variation is in the atomic dimensions. Furthermore, the electrons revolves around the nucleus many times in a second. As for example, the hydrogen 1s electron, that is an electron within a hydrogen atom in its down state or in the first Bohr orbit revolves around 3 into 10 to the power 15 times in a second. They make so many revolutions in a second. So the field that is produced by the dielectric is, the field has strong spatial dependence. It is not a smooth field. It has strong spatial dependence, as well as it will have strong temporal dependence. But we are interested in electrostatics, so the field as a whole must be electrically time independent. Now, if we want to describe this situation in a satisfactory manner, then one must be taking into the phenomenon of atomic dimension, and this is beyond the scope of electrostatics. But we can tackle the situation in a tricky way. In electrostatic, we measure the field by using apparatus which is of macroscopic dimension. Say we want to use a probe to measure the electric field or potential difference. The probe has a dimension few millimeters across, which is much larger than the atomic dimension. So the field that we are considering is a macroscopic field or measuring a macroscopic field. Say for example, when an elephant steps on the ground, he could not feel how many ants it is smashing by the step. Similarly, when we introduce a probe, we do not realize this spatial dependence, and since the time of measurement is also involves few milliseconds or so, which is much larger in comparison with the temporal variation in atomic scale. So what we actually measure is, we measure a field which is an averaged over the atomic fields, averaged over spatial dimension, macroscopic spatial dimension, and time over time, which is much larger in comparison with the time period of atomic phenomena. So we are considering a field which is time average value, so it is smoothed out in space and time, and the field that we will be dealing with will have variation in space but not so much variation. It will be a smoothed out field. Roughly speaking, it will be a smoothed out field. Now the problem is how to tackle the electrostatic problem in a macroscopic sense. That to deal with electrostatics in vacuum, there are two experimental things which guides us. One is the introduction of the concept of dielectric constant. Dielectric constant or relative permittivity. It is a dimensionless quantity, and secondly is the polarization. Let first we describe this thing. Consider a parallel plate capacitor. A parallel plate capacitor comprising of two parallel plates, each of area A each of area A. They are separated by a distance g, and a charge q plus q is given one plate and a charge minus q on the other plate. When the space in between the capacitor is vacuum, we find that capacitance of the capacitor C0 is epsilon 0 A by D, where epsilon 0 is the free space permittivity. If we fill the gap between the plates by a dielectric, then we find that the changed capacitor C is greater than C0. That is to say that if we have free space between the plates, it is the capacitance, and when the space is filled up by a dielectric, this is the value of the capacitance. Since the charge on the plate do not change by the insertion of the dielectric, we conclude that it is the potential which changes. The potential changes. It is found that if we have a potential difference P0 between the plates, when we have vacuum between the plates, and V be the corresponding potential which is obtained by inserting a dielectric, it is found that V is less than V0 by a factor K, which is the characteristic. This factor K is a characteristic of the dielectric under consideration, and it has almost constant value for moderate values of V0. This constant is the dielectric constant or the permittivity. If we consider what will be the change in electric field? Since the separation between the plates is constant, and electric field being the negative gradient of potential, that is E in this case is minus V by D, we conclude that the field will also have such a variation, that field between the plates on inserting the dielectric, if it is E, then it is less than its corresponding value in vacuum. The corresponding value in vacuum is 0. This is one phenomenological way of accounting the effect of dielectric in electrostatic formula. That is, if we have two point charges Q1 and Q2 separated by a distance r, they are separated by a distance r. When the medium in between the charges is vacuum, the potential is for vacuum, the potential is Q1 Q2 by epsilon 0 r, and the field has the variation Q1 Q2 epsilon 0 r square. If we place the same two charges with dielectric, the potential becomes Q1 Q2 by epsilon 0 kr, and the field becomes Q1 Q2 epsilon 0 kr square. This is the change. So to say, we can take care of the effect of dielectric in this fashion. It is found that K is another way of writing the relative permittivity. That is, we can write epsilon 0 K as epsilon 0 Kr as epsilon, the permittivity of the material medium. In general, the permittivity or dielectric constant of vacuum is 1, and that of air is very close to 1, and all other material will have higher values of value greater than 1. So for example, water K is approximately 80. So note that K is a dimensionless quantity. K is 80. So when a sodium chloride, this ionic compound NaCl is dissolved in water, the force when the electrostatic force between the Na plus and Cl minus when they are in vacuum was this. And when this material is placed in this ionic salt is placed in water, the force between these, the attractive force between these two reduces by a factor of 80, which causes, that means in water these two, the cation and cations are much loosely bound, and that causes their dissociation. This is one way of considering the effect of dielectric constant in the macroscopic theory. Next we come to the concept of polarization. In this phenomenological aspect, consideration of dielectric does not look into the matter of what is going on there. Now we come to the polarization. Polarization means the dielectric is made up of atoms and molecules, and when they are placed in an electric field, there will be a changed orientation. Orientation of the charges will be modified in presence of the field. First let me say that this is the original material in absence of field, and due to the presence of the field their charge distribution will be modified, and the field and EM will be due to this modified charge distribution. How to calculate this modified distribution? Since the material has a complex geometry, it is not very easy to calculate the field in practical purposes by analytical methods. So what one can do? One can use a multiple expansion. In the modified charge distribution, we have a modified charge distribution, and we perform the multiple expansion for this induced charge distribution. Since the material as a whole is made up of either atoms and molecules, they are electrically neutral. So if we expand in multiples, the monopole term will not contribute because the system as a whole is the charge neutral. So the most important contribution will come from the dipole, and we neglect the terms or contribution of the higher poles because they are for dipole the variation is of this form, and this is for the dipole, and R, the field point where we are interested in finding out the field, it is of the order of centimeter. It is of the order of centimeter, and this is of the order of nanometers or even less. So it is it is sufficient to keep the first non-vanishing contribution to the potential, that is the dipole potential. We are neglecting quadrupole and octuple contribution because of this logic, and this approximation theory is known as dipole approximation. So our main task is to how the dipoles are created within a material. The polarization, let us consider an atomic system in which the electron revolves round in circular orbit. So this is the position of the nucleus, and electron revolves round the nucleus in circular orbit. Since it executes of the order of 10 to the power 15 revolution per second, we speak of average position of electrons, so to say the center of negative charges. Obviously, the center of negative charge S minus coincides with this S plus, so no dipole is created. So such a material have no dipole moment when there is no field. If we apply an electric field in this direction, then the center of positive charge, where it was originally over here, it will be shifted to there. It is the center of positive charge, and the center of negative charge will be displaced in the other direction. So this will be the center of negative charge. Since the atom as a whole is electrically neutral, so there will be a separation delta which is directed from negative charge to the positive charge. So delta, and so a dipole will be created, and the dipole will, this atomic dipole will have a moment Q times delta, and we could say that the atom is polarized. It is generally found that this polarization is proportional to E, and we introduce a factor alpha called atomic polarizability. Atomic polarizability. Such types of atom, the atom that we have considered, do not have any permanent dipole moment. Only dipole moment is induced when there is a field. And if we have the field in this direction, the field due to the dipole will be in this direction. So EM will be in this direction. So the resultant field within the material will be less than the applied field. Note that in the case of conductor, due to the presence of plenty of electrons, the conductor could cancel the entire field within its body, so the field within the conductor is zero. So we can consider another molecular system, the carbon dioxide molecule. It is found that the carbon dioxide is a linear molecule. It is a linear molecule, so the molecule is formed and there will be a dipole moment in this direction P, another dipole moment in this direction. Due to the symmetry, the two dipole moments are equal and opposite, and the carbon dioxide molecule will have no dipole moment in absence of field. In other words, we can consider that the time average value of the center of negative charge and center of positive charge coincides at the same point, so there is no dipole. When an electric field is applied in this direction, this one will be shifted there, this will be shifted there, and this will be shifted there. That is, this bond will be stretched longer, and that will be compressed, and that will be compressed. So in this case, the two dipole moments will not cancel each other, and an induced dipole moment will be produced. Another way of looking at the situation is that there will be a separation, shift of the center of negative charge in opposition to the electric field, and shift of the center of positive charge in the direction of the electric field, so an induced dipole will be produced. We call such polarization as deformation or electric polarization. And such dielectrics are called non-polar dielectrics. That is, they do not have any permanent dipole moment in absence of field. The entire dipole moment is generated in the presence of field, and it is the induced dipole moment. Now come to the another type of polarization called orientation polarization. We consider again an atomic system in which the atom and the electron revolves around the nucleus in an elliptic orbit. So this is the elliptic orbit, and it is the center of the auxiliary circle. The electron moves around this. So this is the average position or center of negative charge, and the positive charge is at one of the foci of the of the ellipse. So already they are separated by a distance delta 0. So such atoms have a dipole moment even in absence of the field. When an electric field is applied, what happens? Two things happens. One is there will be a change in the bond, the change in the separation of these two, that is the separation between S minus and S plus will undergo a change, thereby some induced dipole will be produced, as in the case of non-polar dielectrics. And secondly, if we have the dipole moment directed in this direction and the field is in this direction, this is the dipole moment. So this is minus q, this is plus q. So the field, the force will be in this direction, and there will be a tendency of rotating the dipole or aligning the dipole in the direction of the field. Such type of material are called polar dielectric, and they have non-zero dipole moment per constituent even in the absence of electric field. The corresponding molecular counterpart is uh, water molecule. It is found that the electron crowds over the oxygen atom so that it can be treated as a negative center. It is a positive center, so two dipoles will be produced uh, in this fashion, and the angle between these two bonds is 105 degree. So the resultant P1 and P2 is P, which is P1 plus P2, and the magnitude of P is 6.2 into 10 to the power 30 coulomb meter. This capital coulomb meter. So water molecule is a polar molecule. It has a non-zero dipole moment even in absence of any electric field. In general, it is found that due to the thermal agitation, if we consider a volume which may be of the order of 10 to the power minus 6 centimeter cube, still it contains around 10 to the power 17 molecules. If we consider a small volume like this, macroscopic volume element which contains a large number of molecules, due to thermal agitation, these dipole moments will be distributed in random in space. So some will be directed towards east, some north, some vertically upward, some vertically downward, and so these dipole will be oriented in all of the 4 pi solid angles. So the vector sum of the dipole moments of all these polar dipoles within volume dV is 0. When some external field is applied, the external field will try to align this dipole in the direction of the field, but this tendency will be opposed by the thermal agitation. So an equilibrium will set up, and we will have a non-zero dipole moment when averaged over this. If we go on increasing the field strength, the strength of the externally applied field, it will be found that the more and more dipole will be aligned in the direction of the field, and there will be a minimum value of field, external field, when all the dipoles are aligned parallel to the electric field. This is called the saturation polarization. This value of the electric field required for the saturation depends on temperature. Higher the temperature, higher will be the field, electric field required for saturation. So this type of dipole, this type of dielectric, whose constituents have non-zero dipole moment, but when averaged to a non-zero dipole moment even in absence of electric field, but when they are averaged over a macroscopic volume element, the resultant dipole moment is 0, is called the polar dielectric. In presence of the field, predominantly the orientations of the dipole in the field, direction of the field takes place. Nevertheless, there is the induction effect, that is the effect that we observed in the case of non-polar dielectric. In analogy with the paramagnetic materials of magnetism, such types of polar dielectrics are alternatively called paraelectric materials. Paraelectric materials. There are other types of polarization, that is called ionic polarization. Ionic polarization occurs in systems comprising of ionic bond, as for example NaCl. It is formed in it is an ionic compound, that is the bond between sodium and chlorine is an ionic one. If we have a positive charge around it, then it will have a field, and this field, due to this field, the other atoms will be oriented in this fashion. plus minus. Such types of orientation is called ionic polarization, which occurs in ionic compounds. Another type of polarization is observed in ferroelectric materials. Ferroelectric material. The ferroelectric material has non-zero dipole moment even in absence of the field, but over this, when we consider a macroscope, the average of dipole moment over the molecules within delta V, it is found that the corresponding dipole moment delta P is not equal to 0. That is to say, the ferroelectric material has their spontaneous magnetization. Some molecular field is produced within such material which aligns the dipole in its direction. That's all about the phenomenological description of this. Uh, uh, One way of considering the dielectric effect is through the dielectric constant, and the other one is the microscopic level. There is polarization effect is produced, and the effect of this microscopic phenomena is taken into consideration by the polarization vector. Let me define polarization vector P. If we want to find out polarization vector at a point R, we consider a macroscopic volume element around R, and we sum over the dipole moments of all the constituents within this delta V, and we find out that the dipole moment delta P is equal to the average or the vector sum of all the dipole moments within this. And we call polarization P at this point R, is limit delta V by V tends to 0, 1 upon delta V summation over I, ER. This is the polarization. It is a macroscopic quantity. We could describe the effect of dielectric through two quantities. One is the phenomenologically introduced dielectric constant, and secondly is the polarization. The effect of microscopic polarization is taken care of by a macroscopic quantity. You know that, notice that the delta V does not tends to 0, because we have considered delta V should be so much so that it accommodates a large number of molecules. Since a molecule has a finite volume, delta V cannot go to 0. But the delta V is indeed negligible in comparison with the volume of the material. So here we have written it. Let me write it. It is delta V by V tends to 0, or we say that delta V is a macroscopic volume element.